So we were here and we were doing this image restoration. Okay. So we said if the image has some problem, okay, let's talk. So how to restore it back? What are these problems? You have seen quickly. The model that we have to use is this one. So we have either the degradation model, which is some degradation due to, although this whole is called the degradation, this edge and the noise, addition of noise, the whole thing will be called degradation. But the way it's been applied to the image is different. Like for example, this type of degradation is a kind of operation that is a convolution operation or the filter operation applied to the image, and then there's another operation that is addition, which is we call it noise. Okay? This comes from the system itself. Okay, let's say you are transmitting or you have a problem in the camera. It can be either this or can be both. So we have seen some of the in the last set of slides, last lecture, we discussed without this type of degradation, which is the convolution problem. We just say that we have an image and we have a noise that is being added to the image. Okay, and we have seen some filters. First, we have definitely discussed some noise, which can be random noise with certain periods like uniform, relay, Gaussian, and okay, and but also these are a kind of a group of noise, and a filter that works for one of them will work for all of them. Then we have another set of noise which is like sorted filter, which behaves differently than this type of noise, and then we have other one which is called a periodic noise, which is again a different kind of noise. So it depends that which type of noise you have, and based on that you design a filter. Okay, so it's necessary to find out the type of noise. How to do that? We can either have this approach to the system that we have and try to find out that which type of system we have and which type of noise we can have. And the second thing is we use a part of the image, okay, and try to find that which the part of the image that we know that, let's say, a constant intensity image, and try to find out which type of noise it is by plotting the histogram of that noise. Okay, fine. So let's move forward, and we were discussing the type of filters that are suitable for this type of noise. Okay, so one is the linear filters, which are four types. There are four types. Okay, so we have a thematic filter, we have geometric, harmonic mean, and contra harmonic mean, which we already have seen last lecture. Then we have border stripping, which is a non-linear filter, and median, min-max, midpoint filter, and alpha trim filter. And then we have adaptive filter. So we just stopped here. So just quickly, we just recall what are these. So these are the type of filters. This is mean filters. It's very obvious. Then you have geometric mean. Instead of summation, we take the multiplication and take the analog. From here, it's very clear that if you have a paper noise, will make this term equal to 0, because paper is making the pixel 0. So if you have power of a paper noise in any of the pixel that we are taking, okay, in the image, that will make this term 0, and if this term is 0, the whole term will be 0, which means that this is ineffective. Okay, then we have this filter which is called harmonic filter, and here also the if we have paper noise, that will make it infinity and whole term will be 0. So it means that if your pixel is 0, that will make this again 0. So it is again not effective. Okay, fine. So then we have a contra harmonic mean filter, which is a kind of a filter that by adjusting the power, I can make it good for either paper or salt, but not both together. Okay, if Q is positive, what it means, if Q is positive and it's good for to eliminate the paper noise. Why? Because if Q is positive, paper is 0 values. So in summation, the 0 values will not be counted. Only the non-zero values will be counted, right? So in this way, it eliminates the paper noise. But if it is negative, so the salt noise which is the high values 255. Okay. So if Q is negative, okay, that will make the significant. No, so if Q is 0, this is equal to the simple mean filter. If Q is -1, it's equal to the harmonic mean filter. So it has some qualities, and we have seen that if we have the Gaussian noise with zero mean and variance, so if we apply the mean filter, geometric mean filter, we get some. In geometric, it's somehow better. Here, it's not very obvious. Definitely need some quantitative analysis to show that, but geometric mean will be somehow better with it. Simple mean. Similarly, if we have the salt and paper noise, so we have paper, the salt. So for the paper, we have to use which type of filter? Yes, we have to use Q positive, or we have to either use, if you want to use a simple filter, that is min filter, right? Min filter for the paper. Okay, so we added a paper noise, here we added a salt, and these are after the filtering. Using the same contra harmonic filter with Q equals to 1.5 for paper noise and -1.5 for. Okay, or if you don't want to use this, what type of filter you will use for paper? Max, and for salt. Then okay.
Can you go back to the slide? I want to see the difference between the original one and the.
Which one? This one?
The image, yeah. What's going on to the next? Okay, so there's some difference between the original image and after the filter.
It's not 100% correct. But if you select the wrong Q value, the image will be even worse. Okay.
Setting the Q values would be randomly.
Yeah, you have, it's again not randomly, hit and try. But I know that for the paper, I have to make Q positive, not negative. This I know. But
Yeah,
how much?
we will.
Yeah, but how positive? Yes, you have to do some experiments. Okay. And again, as I told you before, in image processing, the main problem is this, that most of the values, they are not actually, I cannot find it statistically or some other way. Yeah, you have to do as tune. This is the problem. Even if, like, the other problem is that to find out quantitatively how the image is improved. For example, if I use SNR, or maybe you're familiar with SNR, right? SNR, symmetric ratio. For a simple error, let's say simple error. If I process an image and my simple error is what? Just subtraction, and it is minimum, still maybe that image is not good for me. Okay, why? Because maybe I use a lot of information that I needed it, but because of filtering operation, I just reduce. So it's like a type of compromise. Sometimes I see visually and also see the difference. Okay, mathematically. That's right. So and that's why if you see the papers, they use a lot of metrics, and I will discuss some of them here. They use error, they use mean error, they use also absolute error, they use which we call it SNRP, SNR as well, and then SSIM as well. So there are a lot of metrics. There are a table of metrics that they use just to prove that if the filtering operation is better in all respects, it means that this filter is better. Okay. Okay. So the other type of filter that we saw was non-linear filters. So we have median filters. We take the median value, then we have min-max, Then we have midpoint. We did not discuss it in the previous chapter 3, which is just taking the max, min, and I just do all these operations like the way I did it in the mean filter. Remember that? I take a box, taking a box, doing all these operations. This one, the previous one, and even the further. Okay. So that's why I'm not discussing it on the image, but I'll have one example that I'm discussing.
But then we used to have the kernel, so we know the kernel is only 3 by 3.
Yes. So here also either 3 by 3 or 5 by 5 is up to. Let's assume 3 by 3. So all the operations are on 3 by 3. Okay. So that's why this SXY is actually that box with 3 by 3. Okay, oh fine. So alpha trim, we again discuss it. We instead of taking the mean directly, I just discard the mean and maximum values, some of them. Okay, and why I'm doing this? Just to avoid any sort of paper type of noise or any impulsive noise. Okay, and so it depends on value of D, that how many values I discard. So first I take the box, sort them. Sorting is important. If you don't sort them, discard the min max, you cannot discard, right? You have to sort them, minimum and maximum. You have to remove and then try to find a mean. Okay, so this is again, as we discussed last time, we can also apply the filter several times in order to get rid of some of noise, and we have seen that there are some. If I apply the median filter for the sorted paper, you can still see there are some noise here, which is removed after again passing it to the median filter. You see them, okay, some of them, and here it's being removed here, but still we have one right here, okay, which is removed. Okay, but how many again? If you keep on doing this, you will lose the information. So we have to somehow compromise. It's like overfitting. Okay. So,
for deciding which filter or which output value of images is best is okay to us. How we can evaluate how am I get the best.
there are some metrics, as I told you. Error is one of them. Mean square error, mean absolute error. These are the metrics that we can use to find out which one is best.
Okay. What about the visualization of each image?
That yes, that's also there. Should be there. So you have to visualize. Maybe let's say I zoom in a part of it, see that are the textures or some of the edges are preserved or not. Okay, so I like looking at the whole image. I may not get the actual value, but see sometimes I get it. If you see this is better than this, yes or no? Why?
At that point.
Yeah, this is much more like edgy, but this is it actually the edges are even darker. I don't know what. So it means that this is better.
So it depends sometimes on the needs.
Yeah, it's of course. Of course.
Contrast enhancement, I think, will be.
Yeah, much okay.
Now, before this, my question: how do some of these sort of the points survive? Why majority always appear except for the items? It's a special purpose.
Because yeah, the main problem is that sometimes if what I'm doing to remove the sorting paper, I'm taking either min max or median. So what if, and this is our next filter as well. What if the median itself is a sorted paper, or max itself is a sorted paper? Okay, so it means that if that's sorted paper, it means that this pixel will come here, and this is our next filter as well. Okay, but anyhow, before that, we just discussed one case of mixed noise in which we have uniform noise, zero variance and zero mean and variance 800, and plus sorted paper. Okay, with some probability.
Just was wondering, because instead of doing the whole process for the whole image, is there a way to identify, like, scan the image pixels and then identify where is the sort and just act on, on that one? Yes. I don't need to do the whole thing.
This is what the next filter is. Yes, we have the method for that. Okay. Okay. So we have the image corrected with the uniform noise and then the sort and paper noise. Okay. So this is image plus uniform noise and then plus sort and paper noise. Okay. And then we have to see that if we apply different filters, like for example, we apply first the mean filter. So if you see that it's trying to smooth out, but because the mean filter is not good for sorted paper, so it's not still good, but it's smooth the image. Then we have geometric mean filter, and it makes the things even worse because we saw that geometric mean is not good for paper noise. Okay, so that's the problem. Then we use a median filter. Median filter is good for sorted paper, but not for a random type of noise which is uniform noise, right? So it means that it somehow make it good, but still not better. But however, the alpha trim filter, if you remember, we excluded the two extremes, so it means that we are excluding the sorted paper and we are taking the mean. So we are doing the two things together, which is much better, right? Okay. Fine. So again, how to apply these filters? It's very simple. As we are applying simple mean filter on an image, we are applying all the filters like this. And these are some of the examples. Let's say I'm focusing this pixel. So I will take a 3 by 3 filter. Okay, the mean filter, how I can do? I take the sum of this divided by 9. Okay, then geometric mean, multiply all of them and power by 1 by 9. Okay, and I get the geometric mean filter. Harmonic mean, again, I have to take 1 over all, sum of them, 1 over each pixel, sum them, and then
3 by 3.
Yeah, which is like 9, the total number, 9 divided by the sum of that inverse. Okay, to get the harmonic. Similarly, contra harmonic, same. You have to sum them. Q is equal to 1 means that sum of the all pixel, and by taking the square, because it was, if you remember, what was the formula? Remember? So if it is Q is 1, it becomes square. So I have to square all the pixels, sum them, and here sum only all the pixels, divide the 2 to get the value. And similarly for other Q values of Q. Fine. Here for -2 again, it is for -2. Similarly, median, take the median of this. We did this before. Max, min, and then midpoint. We take the maximum. We take the min divided by 2. Get the midpoint. Alpha trim. We get the summation, but excluding this. So first we have to take all these values, sort them. And for example, if I told you d is equal to 2 means that 2 from the max, 2 from the minimum. I just remove them, eliminate, and the rest I take the mean. And now there comes some adaptive filters, because as all these filters, they assume that the image, the filter is applied evenly to the image. Okay, then if you have a mean filter, it's been applied all over the image. If you have a max or medium or whatever filter, I'm just taking all the image same. I'm not distinguishing between the different parts of the image. So adaptive means that it will take this type of things into consideration. Okay, that maybe not all parts of the image needs the same type of filter. Okay, so one is called adaptive local noise reduction filter, other is called adaptive median filter.
What's the difference between say local?
Local is local. Local to the section that we are taking. Let me discuss and you will find. Okay, so in the adaptive local noise reduction filter, what we have is there are some of the points that we need to address, and based on that points, I will mathematically restore the filter. Okay, so what we can do, the first thing is if the noise variance is 0 in the section, if the noise variance is 0. So I have an image, for example, right here. Okay, so for example, if I have an image here, okay, and previously what I'm doing is that I am treating all the section of the images same, but maybe in one section I need to, there's no noise or less noise as compared to others. So based on the severity of noise, I apply more filtering or less filtering. So this is what it is. So maybe here less noise or no noise, so I don't need to apply. But here, if it is more noise, I need to apply strong filter, right? Okay, so similarly here, if there is no noise varies in that section 3 by 3, I should just make that section equal to my output. And you take this as this section as it is. Okay, as it is. Okay. Similarly, if the local variance, I calculate the variance in this one, and if that is relative, is high as compared to noise variance, what it means? If the local variance here is high as compared to noise variance, and it means that what it means?
I need to do noise separation.
Less noise or more noise?
Yes.
It means that this is less noise, right? Because if I take a local variance, here local variance, fine. So this variance has the variance of the image plus the variance of the noise. If the addition of the image variance and the noise variance is higher than the noise variance, means that the noise is less. So what I want is that I want to do the filtering, but still I want to return a value that's very close to the original image. See, so if I take the variance of here, this section, which I call it sigma, let's say sigma sxy. Okay, what this variance is about? What it contains? Variance of the image and variance of the noise. Okay, if that is higher than the variance of the noise, it means that noise is less. Yes or no? So see, we have 3 cases. One is that we have variance equal to 0, which is no noise. Okay. The second case is there is sigma s, which is greater than 0, but this is the case. Okay. If that is the case, then it means that there is some noise inside. Okay. You have to separate this condition from this condition. And this is a special case when this is 0, no noise. Okay. Just a second. If that is the case, it means that there is noise, but less. Now if two variances are equal, what it means? Portion of the image and the noise. If they are equal, it means that there is strong noise. This case is a strong noise because the variance of portion of the image equal to variance of the noise. So it means that the variance comes from the noise only. So for noise, how we estimated the noise? Yes. Okay, one is either from the system or I take a portion of the image and say that okay, this there is intensity, so I can just plot it. From there I can create it. So I have the noise variance. Okay. Yes, and then I compare this block with this block. If the noise variance is 0, means there is no need to filter. If the section has the variance higher than the noise variance, it means okay. So it means that we have some noise. But if they are equal, it means that it's pure noise. Okay. So if that is the case, we have to do some strong filtering. Okay, agree with this? Okay. Okay. So now see, with these 3 conditions, I come up with this equation. What it means that if the noise variance is 0, okay. So see, if I put a noise variance equal to 0, the estimated is equal to whatever we have. This term will be 0. Second, if we have a local variance higher than the noise variance, okay. So this is higher than this one. So what we have? We are taking this one, which is like this term has some effect, but has a less effect on this term. Okay. Now the third case is if 2 variances are equal. If 2 variances are equal, what we have? This is 1. This will be cancelled with this one, right? So what we have here, this is the mean. Okay. So we will only left with the mean value. So what we are doing is, if the noise is strong, we are just doing the mean filtering. If the noise is less, we don't need to do anything. Or if it's 0, or if the noise is less, we have to do in between. Now one case we did not discuss, and we said, let's say if noise variance is greater than this one. Okay. Now the question is why? Because the noise variance plus this, so it should be always greater. The problem is that all these variances are the estimation. They're not real. If you have the real, yes, that's the case. But in reality, I'm estimating this. I'm also estimating this. So by mistake or by my estimation, this becomes greater than this one. If this becomes greater than this one, this term will be greater than this term, and you get a negative value. Okay. So it means that this system becomes non-linear system. Why not? Why now? The question is why non-linear system? Because the input value was the positive, but output we are getting the negative. Okay, so linear system is a system. If you multiply something at the input, output also multiply with this. But we did not multiply with negative with the input, but output becomes negative. So it becomes a non-linear system. Or in other words, we are getting a negative values which was not there before. So we're taking the wrong information. So in that case, when the sigma this is greater than the sxy value sigma of the portion, then I should take it equal to 1. The whole ratio. So if I have an example, let's say I have an image. This is 4 by 4. I already calculated the noise variance to be this. How to calculate it? The method is already discussed. Okay. So what to do? In order to do this filtering, what things I need? Mean of the image, and also I need the variance as well. Okay, so I start by using the formula of the variance, which we have already discussed before. Okay, so I take the segments and take the variance of each of these segments. Okay, and let's say if I take the segments, take the variance of this assigned to this value, then I slide it. So in that way, I will find the variance of the image. Okay, similarly for the mean, take the mean for each of the block. Okay, once I have these two, I put it in this equation to find out to estimate the image. Yes or no? Yes. This is just like point by point. Huh? Yes. Is this clear? I think this is just a calculation. I just try to find the variance of this image and then try to find, and also definitely I have to do 0 padding, which have already been done. Similarly, the mean, okay, the whole mean, which is this one, and then use this formula to find out the estimated image.
This is fine. 2 slides before.
2 slides before?
Yeah. This slide. I understand some noise, but I still don't understand how it's calculating the variance for one section, which includes the noise and the variance of the image, and then you compare it to the noise of the image. How can I do that? How do I do this calculation? How does that? It doesn't make sense to me. Why I'm doing it? I'm trying to find out I have no noise or high noise.
Yes, or medium. So this thing, first step is this calculation of the noise values. Okay, how to calculate this? You have image and we have discussed this. Fine. Now you have this. Now I am taking this filter and moving along the image. So let's say I'm here. So I will calculate the local values. Okay. So one is that if the noise value is 0, which means that there is no noise. Okay. This is the minimum, the one extreme. Okay. Then we have either this is desired, then it means that we have some noise, which makes sense. We have image plus noise, so it will be great. Okay. But again, since we are estimating, that's why we can have even less than that as well. Okay. But that is different case. Okay. So if that is greater, that means we have noise. The other case is if this is equal to this. If this is equal to this, it means what it means is that it's pure noise. Okay, or noise is dominance. Okay, the values of the image, variation of the image is not visible because the noise is so strong. You get that point? So this is the other extreme, and this is in the middle. So once we have 0, we just get the same image because this term is 0. When we get the two noises equal, then it means that this will be cancelled with this one. Okay, the other extreme, and we will just find the mean at that section. It's not for whole image. It's that section. Okay, and if in the middle, then we have to do some portion of this added to the image. You see what I'm saying? Okay, so there again, this, we are just doing the calculation, and this is our point by point calculation. Okay, all these calculations are some nice calculation. So here again, we use which type of noise? Okay, we take Gaussian noise. We use mean filter here. Yes, this is simple mean, arithmetic mean. Then we use geometric mean, and then we use adaptive noise mean. So if you see which one is clear, you see here it's more smooth. Okay, here it's better, but again the edges become darker. Fine, but if you use this adaptive one, you can see that it results a lot of details. Okay, then again the last filter that is in the spatial domain, and then we move towards the frequency domain filters, is adaptive mean filter. It's again the filter. The question was that when you're applying the median filter, why we have still sort and paper? When you're already applying the filter, why still some of the pixels? So the answer was that the median, maybe what I'm taking in the median filter, I'm taking the median value. But if the median value itself is either 0 or 1 or 0 to 55, it means that it has a sort and paper. Okay, so for that case, what I will do, I have two levels. First, I have to check the median if it is in between min and max, not min and max, but in between. So if it is in between, I will go to next level. So it means what this condition checks that the median is not salt or paper. So I go to level B. Again, check also the pixel that I am concentrating to be in between these two. Okay, if the pixel itself that I am pointing towards is in between min and max, it means that pixel itself is not salt and paper. So it means that I don't need to do anything. No need to do any filtering because that pixel don't have salt and paper noise.
No, yes, this is the minimum and maximum for the whole image, or only, not only for the pixel. So in that case, possibly yes, because I consider the point is only one.
Of course. Okay, I have the example. I'll show you. Yes, it will be just that. Okay, so the idea is I have to see the pixel where I am applying the image. If that pixel does not have the salt and paper, I don't need to do anything. But if it has the salt and paper, then I have to see the median value, that the median value itself should not have a salt and paper. If that is the case, then I have to apply the median filter. Yeah, it's a kind of a median filter with some conditions.
The salt and paper will take what? The 9 pixels, or most of these 9 pixels that we are looking for? Or
not most of, they depend on the probability, but some of them.
But
not all of them.
could be part of the image.
Yeah, this can be a part of, maybe 0 and 1 can be a part of. But however, we don't know. Okay, so that's why we are trying to make sure that the other pixel should not be affected. Okay, so again, this is the median filter with some exception. Median filter, if I have to check if the pixel I'm focusing on is in between max and min, I don't need to do anything because it's not a part of solid. Okay, but if it is not in between min and max, I have to find the median. Okay, with some condition. And again, the second condition, the second condition is also I have to check that the median itself that I'm calculating should not be the spot of salt and paper. So for that, I have to make sure if that is not the case, I have to increase the size of the filter itself from 3 to 4. And I will just show you example. I think it will be clear. If it blur, it will smooth. The good thing about this filter is it will smooth the image and also it will remove the salt and paper. And let me give you an example. Let's say my focus is this pixel, and I will start with 3 by 3, and assuming that the maximum allowed mask for the size is 5 by 5. So from 3 by 3, I get maximum is 5 by 5. Okay, after that, it's not allowed. Okay. So I will start with 3 by 3. So I have 3 by 3 around this. So what was the first condition? I have to. Okay, so the things I needed is I need the min, I need the max, I need the medium, and the pixel itself. So what is the minimum here?
Minimum
1. What is the maximum? 7. What is the median? Again, you have to sort it out, and you can see that this is 7 here, the median. Okay. Then we have, and pixel itself is 7. Now we have this value. Now go to the condition. First I said the first level is that the median should be in between min and max. But median is 7 and it is not in between. It's equal to the maximum. It means that the median itself has a which noise? Sort noise. Okay. So what I have to do is I have to increase the size of x and y. This size. I go to another one step further, increase the size, which is 5 by 5. Okay. After that, again I do the same. I find the min, max, median, and the pixel itself. Again can have the condition. So see median in between. Yes, it's in between. Okay. So because of that means that the median does not contain the salt or paper. So I go to other and I check if the pixel itself, which is 7, has the salt or paper or not. Okay, if it does not have it, so I have to take this. But to have it, I have to just find the median. Okay, so that is not the case. It's equal to the max. It means that it has a paper noise. The probability is that it has the paper noise. May not have the paper noise, but I have to make sure that there should the noise should not be there. Okay, so the output is 5 because the median. Now it's clear or not? Okay, so in other words, just to summarize, I have to take this pixel if I am very much confident that this is not salt and paper. But if I'm not confident, I have to take the median. This is what the conclusion is. This is equal to this. Output is the median. Yes, in this case. Okay.
Because here I can understand is if it is in between, the minimum and maximum value will be. Now, if it is not in between,
Then increase the size. Else increase the size. Just to make sure that it should be in between. Okay. But we have to stop the size at some point, and then we don't have any choice, so we output the median. Okay. So this way definitely is not 100% a perfect. Maybe as you mentioned, maybe the noise, the salt and pepper can still be there, but we have to go the salt and pepper. Maybe the 0 and 7 might be not from the salt and pepper, but from the image itself. We don't know, but we want to make probability. That's just. So this is what we have. We have a salt and pepper calculated noise. So we apply median filter and we apply the adaptive median filter. So what you notice here?
the one in the middle is really information is lost.
Yeah, some of the information is lost because we are strongly applying the median filter. So if you see here, as again your question, some of the pixel that belongs to the image, but because of the median filter, it make it 0 because it was black, so it make it 0, which was not the case, and which makes sense. I mean, in this area, if I apply the median filter, there's white and black. So if black, if the white is in the middle, you have to take black. If the black is in the middle, you take black. But if you do the adaptive, then this is somehow better than the simple adaptive. Okay. So I think yeah. So this is some of the filters that were actually we discussed some of them before, and there are some others that we discuss now. Similarly, for the frequency domain, we discussed two new filters. Fine. So let's discuss the frequency domain restoration. Okay. Again, this is the same type of mathematical model that we have to use, but in this set of slide, we will also consider the degradation due to the system. Okay. So, fine. So first we discuss the periodic noise. The periodic noise is the noise that is repeating after some time. Let's say, for example, sinusoidal, right? So what do you think sinusoidal noise is better eliminated in which domain? Okay, because we have a specific frequency generated because of that sinusoidal, which we can just kill and we get the signal. Okay, so that's why periodic noise is being eliminated in the frequency domain. Okay, cannot be done in the spatial. But which type of filters that we can use for that? Either I can use a band reject or band pass or notch filter. Okay, yes, but notch is better, of course, and we will discuss this. So let's say we have a noise that's sinusoidal, so it can be a sine. Sine and cosine in the frequency domain are just impulses at that specific frequency. Yes. Okay, so how it look like? Let's say if you have a sine noise, sorry, cos noise. This is cos noise, which will look like this. This is just for your information that how it will look like. It will look like this in the image, but actually in the 3D it's like a cos repeating. Okay, so because this is a bit confusing, you might be thinking how it is cos. So basically, it's a 3D. If you plot 3D, you can see that how it's. So if I plot the same cos in the frequency domain, I get two pulses, one on the positive, negative. Okay, because of the mathematical, you get two pulses, right? So this is time, or this is the spatial domain. If I take the frequency, I get this. If you have, let's say, 2D, it will look like this here and here. This is V and this is U. Okay, so you get these two, because I showed in 3D. So if I add an image with the periodic noise, which is constant and also normally present in satellite images because of the transmission. Okay, so you get this thing, right? Now, if I check the frequency domain of this, I get this. So it means that there is two pulses which belong to this periodic noise. Okay, and in 3D, I can say that I have an image. This is the frequency transform of the image plus you have a frequency transform of the noise. Yes or no? Okay. Now, in order to get the things back, I can do either a low pass filter or band reject filter, just reject this band, but that will reject all the band, which I don't need. I just need to kill this frequency and this frequency. So the notch filter in that case will help me more. Okay. So what is the notch filter? So here we will use the notch filter as we discussed before as well. But it's notch, it's like all one, but in certain points where we have that noise, we'll get the 0. So this will kill that particular frequency that we want to eliminate. And again, if you remember before, discussed, we can have ideal, Gaussian, and three type of filters. Okay. So if we do the same, this is a notch filter with two black dots. If I just multiply this with this one, it will remove this and unchange the others. Okay. So I get the clear image, and this is after subtraction these two, I get the noise back in time domain. Now, sometimes the notch filter doesn't mean that we just kill one frequency. You can have a certain frequency. Let's say this is the image. Again, this is some sort of, I don't know, which satellite image with the horizontal lines. Okay. If I plot it, I get this thing, and based on my some experiments, I found that this line belongs to these horizontal lines. Okay. So if I just design a notch filter, make this black and rest is white. If I just multiply them, everything is 1 except this. So only I can get rid of this, and here I can. But back to the special domain, I'll get rid of these horizontal lines. Yes or no? Okay. What will happen if instead of killing only these frequencies? Okay, let's say you have an image and the periodic noise, and this periodic noise appears here, these two. Okay, so I have to kill this using the notch filter. Instead of that, if I use I can use a low pass filter here just to extract this one. So what will happen if I do the notch filter, and what will happen if I use the low pass filter? So if I use a notch filter, just kill these frequencies, but I will get this image. But if I use a low pass filter, get rid of this value only, select the middle one, I still somehow get rid of this periodic, but the image information is also lost because it becomes more smooth. Yes. No, this is band rejected. True. Okay, because I reject this whole band. So if I reject this whole band, I get this. Even the same, if you use low pass filter, you will get some of the information of the image also. Okay. So
Does it have to be in a circle?
This circle for band reject, you have to select the circle. So the whole band needs to be rejected.
The same thing for the low pass.
Low pass, yes. Low pass, then you have to pass this here, and the other one need to be rejected.
Can I do a filter with my own shape?
Yes. Okay. Yes. So we discussed the noise here. Now we come to the another degradation, which is the convolution operation from the image. Okay, from the convolution. Okay, the degradation here is because of the convolution operation, or it can be mathematically represented as a convolution operation. But again, convolution operation we have discussed that it should be a what? It should be linear and time invariant.